Okay, so let's just do the little hands up first. Who here has used Cassandra? 1, 2, 3. So we'll spend some time introducing what Cassandra is. How about Spark? Okay, how about Spark on the batch analytics or Spark on the streaming? So streaming, not many, mainly just batch then? Okay. So a little introduction, just to see why I'm talking about this. So I actually work for a company called DataStax, and this will be the second to last survey. Who's heard of DataStax? Quite a lot. It's increasing. They're quite big in America, and they're slowly overtaking Europe too now. So essentially what DataStax do is they take Apache Cassandra, they take Apache Spark, and Apache Solr and build a product out of it. And that product can be your operational database, but it can also be your analytics platform, and you can add in text search as well. So everything I'm going to talk about today, you can do with open source Apache Cassandra, okay? Open source Spark. It's just a lot easier with DataStax's product, but don't think I'm a salesman. You can do this with open source, I promise. My experience with Cassandra has mainly come from working at Sky. So anyone heard of Sky? Yeah, everyone's heard of it. I say that in a different country, like no. I know. So essentially, Sky moving more into their online television, okay? And when they initially thought, let's do some internet television, no one thought it was going to take off, okay? Surprisingly, it did. Everyone likes watching Game of Thrones on their iPad, so it got busier and busier and busier. They'd originally outsourced a small company to build the platform, a smallish company. That's still the main thing which produces internet television for Sky now. It's this large monolithic Tomcat application backed by Oracle, falls over on a, not a daily basis, but we'll go every 2 days. But what we're doing was we're replacing that system with a system backed by Cassandra. So I can go quite slowly. When I first thought I was going to have to cram this into 30 minutes and then 45 minutes, I thought I was going to have to speak very quickly. And given I've got a northern accent, you probably wouldn't have understood a word. Okay, so but now I've got a full hour because the other speaker dropped out. I can go a little bit more slowly, so I'm happy for questions throughout, so we can make this interactive if you want. So what we're going to do first is talk about a bit about motivation, and I'm going to do that via an example application, which is online, which you can go and play with. And the scenario is doing analytics on weather data. So it's both ingesting the weather data at a high volume, so you need a data store which can take it, but we're also going to do stream analytics. We're not going to go into batch, but the APIs for Spark are so similar that you're pretty much learning how to do batch as well. And then we're going to go into the tech stack. So I'm going to spend a bit more time on Cassandra, given that most people here have not used Cassandra. Then I'll do a little overview of Spark, and then we'll go and look at some code, okay? And obviously, that's a lot in one day. So I'm going to put the warning sign up because I'm going to throw lots and lots of information at you. And I'll be around for the hour afterwards for the beers, so you can ask me questions for hours about it. So, everyone recognize these 3 terms? Yep. This is the last quiz, I absolutely promise. Who here would say they build like an operational system, like backing a website or mobile apps, or like something like what would classify as an OLTP system? A few. How about batch? Who here works with technologies like Hadoop MapReduce and things like that? Who here does the middle one? So people want answers, but they want it reasonably quickly. They want reports. They want like recommendation engines. The one in the middle, so kind of like semi-real-time analytics processing. It's pretty even. So the technology stacks that we use today for these things. So there's lots and lots of databases, okay? A couple of them, say MySQL, Oracle, Postgres, most of them relational. People like Mongo and Couchbase have come into this space. And a lot of these databases you can kind of use for like reporting, right? Assuming your data set isn't too large, you can continue to do reporting style queries, which are going to give you a response time in seconds, maybe minutes. Eventually it'll run out and you'll take all of that data and you'll extract it and you'll stick it into something like a Hadoop. That's actually Storm. And at that point, you've got a new team, you've got a new set of infrastructure. It's probably going into HDFS and you're probably running MapReduce on top. I'm going to suggest something quite different, okay? For the transaction processing, your operational database, we're going to talk about using Cassandra, okay? Open source database from Facebook, but it's changed quite a lot since then. For our batch analytics, I'm going to suggest we're using Spark, okay? And in the middle, to do kind of our, keeping our dashboards up to date to see what our customers are up to do, or working out, the monthly min and max for the weather. I'm going to suggest we use Spark Streaming. And there's an application online which looks a little bit like this, which you can take and you can play with. It uses it's all written in Scala, it uses Akka, it uses Spark, and it uses Cassandra. The scenario is essentially, there are lots and lots of weather stations around the world. I'm not necessarily talking about big ones. It could be Raspberry Pis, okay? They all produce data, okay? I'm assuming they maybe produce, say, an event every hour. But if there's millions of these, suddenly your application, which is going to ingest this data, needs to handle, hundreds, if not millions of transactions a second. Okay? And we can put that into certain databases, but eventually they'll fall over in a heap. Okay? When you get to certain data levels and certain transaction amounts, you'll need to do techniques to make them scale. And you can do that with relational databases, don't get me wrong. Facebook is the prime example that if you put enough effort and money into something, you can make it scale. But they tend to stop being relational databases, okay? You start denormalizing, you start removing constraints, all of these types of things, okay? You start sharding. So we're going to talk about how to use Cassandra for that part. But for the aggregation type of thing, so constantly keeping up to date how much it's rained today, the min and max for the year or the month and all these types of things, that's what we're going to use Spark Streaming for. Now, if this was a longer talk, I'd first show you how to do batch Spark and then saving it back into Cassandra so you could, run your application working off that data that's been produced by the batch jobs. But we're going to skip that and just go right to the streaming, okay? So it's just going to go through this flow. It's going to go through Kafka. It's going to go into Spark, and then it's going to get saved into Cassandra, both the raw data and aggregates and things. And I'm terrible at producing UIs. But if you were to produce a UI for this, it might look a little bit like this, okay? So it's real data, by the way. So it's actually weather data you can get online, historical data. And I've imported 20,000 real weather stations into it. And then there's two ways to ingest data. One is kind of like we actually have downloaded some data from online and we can shove it through it. The other is that we can actually just generate some data. So we can say between this date and this date, make up some weather data. And the idea is that we should be able to build things like this, okay? And these should be updated in near real time. Okay, so within, say, 500 milliseconds, we're going to keep things like the daily precipitation up to date. Okay? If you want to play with this afterward, it is on GitHub, like everything is these days, so you can go and grab it. The dashboard part is actually not quite in there yet. It's in my public fork, but you can go and play with that, and it'll be in the main one within a week or so. So if we're going to build a system like that, we need to start learning about, hopefully, Cassandra and Spark. So let's first learn a little bit about Cassandra. So you might get bored if you're the one person who knows Cassandra. So you've probably used it today, okay? If you use Spotify, Netflix, if you've got an iPhone, you're using Cassandra most of the time. If you Google, say, does Apple use Cassandra, you'll hear presentations online where they're running around 75,000 nodes in production. So it's run at a somewhat larger scale than most databases. Netflix, they run a couple of thousand nodes in production. I came from Sky. They're very modest. It's more like 100. There's lots of finance companies using it because it's really good for time-orientated data, okay? Because you get to pick how it's stored on disk, which is why a lot of people use it. It doesn't matter how the data is ordered. It's just the fact that time series is the most popular type of ordered data. So if you hear the classic Internet of Things, it's used a lot for that because most Internet of Things data is actually time series data. And it's used a lot for things like online gaming because one of the other big features of Cassandra is, have you got a question?
Yeah, you have mobile up there. I'm just wondering if you have some examples of mobile applications that talk to Cassandra.
So the actual iOS operating system itself, the things behind that is Cassandra. So if you can actually find, so that is the biggest one. That's like 400 million users.
So what driver do you use to talk to the iOS?
Correct. So I would suggest, I wouldn't want to couple my iPhone application to a database because I want to be able to change my backend infrastructure. When I say most mobile apps would use it, I would say the services that are backing those mobile apps would be backed by Cassandra. Because like Sky, for instance, we replaced all of our backend services using a completely different technology stack, didn't have to change the front end. If we'd coupled, say, the front end to the actual database running in the back, that wouldn't have been the case.
And what's a nice thing to have in the middle?
That depends on your integrating technology. You can pick, mostly with mobile, the common one is HTTP, simply because everything has a HTTP client. So all of ours was HTTP at Sky. Okay, so sweet spot for data modeling is ordered data, okay? And it's because, and I'll explain how, you get to pick how it's ordered on disk, so you get to do particularly fast range queries, slice queries. However, most people that end up using Cassandra are using it for non-functional requirements. They haven't thought, ooh, my data model fits in here perfectly, like say you might with a graph database. They're typically, say, migrating from MySQL or Mongo or Oracle because they've hit a scaling point, okay? And essentially the kind of characteristics, and I'll explain how, of Cassandra, it has pretty much linear scalability, and that's of durable writes, okay? It's data center aware, it's completely topology aware. And if you've kind of done any studying on CAP and availability, you realize it's pretty much impossible to build an available database if it doesn't understand its topology. I mean, like what its data centers are, what its racks are, what happens when there's a partition between racks, what happens when an entire rack fails. We're going to understand how Cassandra actually handles all of that. And most relevant for this talk is how we can use that data center awareness to do analytics directly on top of our operational database. So, it's about 5 years old. 2 academic-ish papers, because they were not ish because they were done by companies, is most of the theory behind Cassandra. So, I promised I wouldn't do another Hans thing. Who's read Dynamo paper? No. It's a really good read. It explains how to build an always-on database. And typically, you're sacrificing consistency for being always on. Okay? And it was Amazon who did it for their basket service, because they eventually realized that actually if you can't add things to your basket and you can't check out a basket, they don't make a great deal of money. So they'd rather things be incorrect sometimes than to have downtime in that service. The Google Big Table is very much around the data model. So it doesn't use anything from Google Big Table. It uses this very similar data model. So Amazon Dynamo is all about key value store. Cassandra's not a key value store. It's what's called a wide columnar or a columnar store. And that essentially, from a programmer's point of view, is a map of maps. But I'll show you that in an example. Every node in a Cassandra cluster knows which data center it's in and which rack it's on. And the benefits of that is you can run one logical database across the whole world, but each node knows which region it's in, and each client knows to speak to its local local nodes unless they're all dead. Okay? So you can actually run multiple data centers to get your application close to your customer, to your client, to wherever's actually accessing it. That's really important for services like Netflix. You know, you don't want your Netflix to be talking to the American Netflix servers. But again, for us, they don't have to be real data centers. You can make them up, okay? So one really good reason for making up a data center is to segregate nodes so you can run more analytical style queries on them and not affect the performance of your, say, the servers which are, servicing your website or your customers. Okay? So that's what we're going to talk about mainly today. So here's the paper. I'll let you read it now. No, you don't read it now. But it really is a really great paper to read if you're a software engineer. It's not overly technical. It's very much describing a real-life problem that we can all relate with and how they went about designing their database which solves that problem. And there's some proper computer science in there as well. So we're not going to go through it all because we want to get onto Spark quite quickly because we're here for Cassandra and Spark. But I'm going to talk about the things relevant to being able to run analytics directly on top of what is normally your operational database. So we're going to talk about how the data is essentially distributed around many nodes in what's called a Cassandra cluster. And we're going to talk about how the data is replicated to avoid losing it and to handle things like partitions. There's a few parts of Dynamo which Cassandra just isn't. Okay? 2 main parts from my point of view is the fact it's not a key value store. And if you have a distributed key value store, conflicts are extremely important because if the database isn't aware of the data you're storing and people are writing it from multiple parts of the world, if there's a conflict, there's not much a database can do. It's like, nah, the blobs are conflicted. Okay? So to get around that, the Dynamo paper talked about using vector clocks. And that's just a way of working out when there's a conflict and then giving it to the client to, please sort this out, merge these 2 baskets, say. With Cassandra, it's a wide column row. It's wide column store. And you can actually data model around conflicts. And when we look at the data model, I'll show you how to do that. So we're going to start off with consistent hashing. which essentially is avoiding a 1,000-node table scan. So Cassandra is all about building performant queries, which are going to perform the same when you've got 3 nodes of Cassandra, and the same when you've got 1,000 nodes of Cassandra. And there's one thing we definitely can't do if we want to do that, and that's go to every node for any query. We have to be able to pick a single node or a very small number of nodes to either read or write our data. And it essentially does that with consistent hashing. So we take the first part of the key. So here's some data. And this is kind of what I mean by a map of maps. So we've got the first key, which is Jim, and then we've got the age, which is kind of like the second key, and then 36. Okay? And then Jim, car, Ford. Okay, so that's what I mean by, say, a map of maps. The first key, say Jim, Carol, Johnny, Susie, that's what we're going to hash. Okay? And the hash gives us a nice value, and it's actually a 128-bit value, but I don't know how to say these numbers. Well, I could in powers of 2, but it's a 128-bit number. We're going to pretend it's really between a 0 and 1,000. Okay? So we're going to pretend that with Murmur 3, it doesn't, in case you're watching, Jim hashes to 350, Carol hashes to 998, and Johnny hashes to 50. Then each node in this large cluster owns a range. So we might say that we've got 4-node cluster, which would be a very modest Cassandra cluster. We might say that node A owns between 0 and 249. Node B owns between 250 and 499. Or if you've seen Cassandra logos, you might see a ring. That's pretty much what it's trying to tell you. That's what the ring represents. It's this hash ring, okay? So you know that between these two, A and B is owned by B. Between B and C is owned by C, okay? And that means that we can work out, both each Cassandra node in the cluster can work out where the data should be, and the clients can work out. So inside the driver, it executes the same algorithm and can go directly to the node which has the data. So we can see that because, Johnny hashes to 50, it's owned by node A. Yeah?
Quick question. So I understand roughly how this works with Netflix. So you've got 1,000 films and you've got audiences all around the world, and then you just increase the replication and throughput so more users can read it locally. But if you've got something more like Facebook, which is really connected, you've got this person's connected to all those people, and then he's connected to that one person which is in another country, how does it know to replicate just his social network, per se, to...
So we're going to go into replication next, and it's not going to be that clever. You're going to have to design it yourself. Titan, if you've come across that, which is built on top of Cassandra, is like a layer to help you with graph-style problems. And Titan itself is recently, the Aurelius, the company that built it, has recently been bought by DataStack. So within a year or so, there will actually be help to do that kind of thing. But Facebook, that level of scalability as a graph problem is quite unique. But everybody kind of likes modeling as graph. But the only graph databases we have aren't particularly scalable. Okay, they're normally horizontally scalable, not vertically. They're normally vertical scalable, not horizontal. So you always hit like a bottleneck. So if I don't tell you any more about Cassandra, then how fault tolerant is it? What happens if node A goes down? Do we lose our availability? Well, the answer would be yes. And you could set Cassandra up to do this. You get to pick Cassandra's replication. Okay? But if we want an always-on kind of fault-tolerant database, we kind of have to store our data in more than one server. Ideally more than one rack, ideally more than one data center. Okay? We don't have to, but if you want to have an always-up system in CapTherm and AP system, you kind of need to. So how does replication work in Cassandra? Well, there's two ways. There's a stupid way and the clever way. The stupid way, which is also called the simple way, is basically just for setting up a quick dev environment. You never, ever, ever use this in production. You're normally using what's called a network topology. And basically what that does is each node in the cluster knows which data center and rack it's in. You can tell it, you can lie, but you probably shouldn't unless you're doing with this kind of workload isolation. It can also be worked out, say if you're running an AWS, it can work it out based off the region and the availability zone. Or if you're in similar thing for GCE, Google Compute Engine, or it can be based off the IP, or you can be as simple as giving it a property file. Right? And what it then does is it hashes to find the first replica, okay? Then it walks around the ring and then tries to put your piece of data on different racks. So if you ask Cassandra to replicate the data 3 times, and you've got 3 racks in your data center, it will put each piece of data once on each rack, okay? By default in AWS, if you're running, say, in Europe and you've got 3 availability zones, it will treat the availability zone as a rack and the region as a data center and actually store your data across all of the availability zones. So then you can handle partitions between the availability zones or the racks. You can handle 2 entire racks or availability zones going down without losing data. Okay? Unfortunately, though, Cassandra can't create these racks for you. You need to get your ops person involved. Yeah.
One thing I've thought about, I've got clients who are in Asia quite a lot, so they operate in China and Southeast Asia and so on, who are quite interested in Cassandra.
Yeah.
But one problem they have is connectivity between their data centers.
Mm-hmm.
How does connectivity between the replication node affect performance and everything else?
I think the next couple of slides will be pretty relevant for that. So I'm going to talk about a scenario which is we've got 2 data centers, okay? And technically they'd be as 1 ring, but I think it shows it better if we do them as 2 rings, okay? And as soon as they're in different data centers, Cassandra assumes that the network link between them is slow, okay? So it's going to do different things between nodes in the other data centers to nodes within the same data center. So let's pretend we've got 1 in Europe and 1 in Asia, and you get to pick a replication factor per data center. So we can say, we want 3 in each. Or, if you're really paranoid, you might say 5. Odd numbers are really good because then you can work in majorities. What a client will do, okay? The client will know which is its local data center, connect to one of the local nodes. Assuming that you've configured it, it is the default, it will actually talk to a node which is going to handle that read or write, okay? So it's going to connect to that one. Just for this one request, it's called a coordinator. It's not special for any other request, just for this one request. Every single transaction, every single kind of interaction with Cassandra, you pick a consistency. What you're normally trading off is latency versus consistency. By default, it's 1, okay? And we'll talk about the other ones after this slide. That basically means I want one of the replicas out of all 6 to acknowledge that write before you tell me it's really done, okay? And if it's talked to one of the replicas, that's going to get done pretty much right away, okay? And then a whole host of asynchronous replication goes on, okay? So because we've asked for 3 replicas, what that coordinator is going to do is get it out to the other 2 replicas in that local data center. It's then going to designate a coordinator. This all happens at the same time, but I can't say it all at the same time. It then designates a coordinator in the other data center, okay? Copies it over the WAN, the slower network, once. It's then that node's responsibility to then replicate it out to the, however many replicas in that data center. And you can have a different number of replicas in each data center. People often want 3 or perhaps 5 for their operational one where they really can't handle downtime. For batch analytics, they might feel cheap and not want to buy so many hard drives, so they might replicate it once and realize if they do lose a node, they need to rebuild it from the data on the other side. So to probably fully answer your question, I've got one funny slide with cats on first. I often get asked now, is that coordinator special? Is the first replica special? Is that a master? Can I turn that off? All that type of thing. With most databases, there's some form of like master slave or something which means that the ops person really doesn't want you to turn off one of the nodes. That's not the case with Cassandra. It will happily use the 2 other replicas that it designated because they're on different racks. They're all completely equal. The one it originally hashed to can be down as far as it's concerned, okay? So there's no kind of special nodes in Cassandra. For each request, there's a coordinator for that request. That coordinator goes down, the clients will just roll over to another one. The tunable consistency is where you get to trade off this latency and decide whether you want to jump across a WAN, okay? So the default's 1. If you want, you can do all. That would be all 6 in that previous example, okay? You don't really have an available database if you pick all, okay? Because as soon as one node's down, some queries will fail because it obviously couldn't read or write to all the nodes if one of them are down. So you don't use all, okay? That makes people who are moving from relational databases happy for the first day, and then they stop using it. What you normally do is something based on, say, a majority, a quorum. And you have 2 types of these, okay? One is just the simple quorum. And in the previous example, we had 6 replicas, so a quorum, a majority, would be 4, which means that we would have to jump over the WAN for that user transaction to complete, which is slow. What you would normally do is have your local clients talk to the local data center for both reads and writes, and to use something called local quorum, which means get it to a majority of the replicas in this data center. let the other stuff go to the other data center happen asynchronously. The only reason a client would flip data center is if you had a catastrophic failure of all the nodes, okay? That make sense? Answer your question? Cool. If you're interested in a much longer talk on just eventual consistency, this guy called Christos, he's like the head of cloud engineering, he's got a very grand title, head of, I think, cloud engineering at Netflix. And they are constantly running tests where they actually always write at 1, but they actually like are constantly reading it in each of the regions of the world and like seeing when it actually comes out, okay? Netflix are obviously, who reads the Netflix tech blog? Start reading it, it's awesome. Especially if you use things like Cassandra and Spark. They're a huge Spark streaming user. Of course.
You might actually be going there, but so whatever I hash is my key.
Yeah.
That's my searchable parameter.
That has to be included as part of the query, yeah.
Yeah, so I have to be able to hash all my results. I have to search my weight totals. Has to be on the hashing.
Absolutely, yeah. So we're going to talk about data modeling after we talk about Spark, because I'm going to do it based on the example rather than theory. But the kind of no free lunch is the fact that you have to store your data how you're going to read it.
The next one then is, does Cassandra offer the same concept as I want to use the word ready in the sense of the first one to answer gets me a good answer and I can go back. So if I have 100 nodes responding, or X nodes responding, the first one with a good answer, go home and tell the rest to go.
So the coordinator itself can do that. There is nothing built into the client which would do that, okay? You can implement it yourself because it's kind of called I'm not going to go too much into it because it'd be a full Cassandra talk, but you pick the load balancing policy, and there's a bunch of default ones. One is based on the latency of the nodes, and you pick the one that over the last rolling window has been quick. Another one is you just go directly to the nodes which actually have the data and things.
You ask all three, and the first one gives you an answer. You tell the rest to shut down and go home, and then you go.
You can't cancel queries in Cassandra. The coordinator kind of does that. So even if you're asking for, say, a read consistency of 1, it might speculatively ask an extra couple of nodes anyway and give you it back. But there's nothing built into the driver to do what you said. Okay. But most of the drivers are actually open source and separate. So there's Netflix actually have their own driver. So there wouldn't be anything stopping you from doing it. The downside, I would say, would be you'd be overloading the cluster because they'd all start it. But
yeah, if you wanted to do a read cluster rather than a write cluster, in a sense. So I'd like to get a whole large sum of results in the sense of Spark. I'd like to get a large sum of results into my memory, but I don't want to really wait until I get all the results back from everywhere. In the sense of, I'd rather, if somehow one of them's got a faster disk, if it gives me the answers, yeah, okay, I don't need that answer anymore.
We'll definitely be talking about how Spark reads data from Cassandra, because it's pretty important for anything which Spark connects to be aware of how it partitions data and to read it cleverly. But we'll talk about that in a bit. So last section on Cassandra, we're going to skip data modeling until we go to the actual code and how we data model for that problem. It's just roughly about how Cassandra scales. So if I say you know where the data is, the client knows, other nodes know, what happens when it moves? You think, why would it move? Well, one of the reasons for moving is if we add more nodes to the cluster, okay? Cassandra can scale both linearly, both in the data size and the, say the read or write throughput. So there's two reasons for scaling almost, okay? And what happens is, do you know how I told you about those ranges? Each node owns a particular range. The truth is, each node actually owns hundreds of little ranges, okay? It's just that I didn't want to explain that at the time. And when a new node joins the cluster, he basically comes along and can talk to any of the nodes, and you can find out about the topology of the cluster. And it says, oh, give me a bunch of them. And then they get streamed over. While they're being streamed over, the reads and writes go to the original people, okay, the original nodes. They're not people. And then when it's finished streaming, then it joins fully. And the communication between, say, a driver and a Cassandra cluster is two-way and asynchronous. So the cluster can decide to tell the driver something whenever it wants. And one of the reasons it might do that is to tell it about additional nodes inside the cluster. Okay? So that's roughly how scaling works. And it just works in the reverse for taking away nodes. You say, node, you're going away. And he says, oh, I better stream my data to some places. If the node's catastrophically dead, then you actually just tell Cassandra it's not coming back. And then obviously there were extra replicas for the data it owns, and then that's streamed to new owners. So that's as short as I could make a Cassandra intro because we wanted to talk about Spark and the example. Any questions on like pure Cassandra before we move on to Spark?
I have a question.
Yeah.
Can you just contrast the Cassandra implementation with HBase?
So I don't know a lot about HBase. I know quite a lot about Mongo and Couchbase, etc. It's conceptually the same data model. You know, it's backed by HDFS as opposed to Cassandra doesn't use an external storage system. It's completely implemented itself. So it doesn't use, say, Wired Tiger or something like that. So, yeah. But I don't know a huge amount about HBase. So.
If I had a Cassandra,
Yeah.
if I had a Cassandra just as a single node, okay, just going from a scaling point of view versus a plain old relational,
Yeah.
would it be feasible? On the assumption that I would like to scale eventually.
Yes, one of my colleagues always talks about the technical debt of moving database migrations when you become successful. So if you're an optimist, by all means, the issue is that Cassandra removes functionality from you that wouldn't work in a distributed environment. So when you're on 10 nodes, okay, so you're gonna lose things like joins and aggregates and things. So you would be putting yourself through some pain, but with the advantage that you can scale, you can start scaling when you want to.
So yeah, as long as I don't use those original.
Yeah, but the features, we're going to talk about it, why you'd use Spark on top of Cassandra, and it's normally to bring back features that you don't have in, say, that you normally would get in a relational database. So, yeah, the kind of things which you do to a relational database to make it scale is basically what you have to do from the start with Cassandra. So before we jump right into Spark, so is there more questions? No. Before we jump right into Spark, I'm now going to kind of defend Cassandra, why it can't do lots of things, okay? Cassandra's all about what I call scalable, predictable performance, which sounds like a marketing term, doesn't it? But I promise you it's not, okay? What I mean by performance is how quickly does it come back for a read or a write. What I mean by scalable is does it change when the amount of data you've got or the amount of reads and writes you want to do increases, okay? Can I just add nodes to my Cassandra cluster and my 5 millisecond query on my 3-node cluster still takes 5 milliseconds on a 100-node cluster? And the answer should be yes, okay? And it does that by, doing the consistent hashing, going to a single node or perhaps 2 nodes if you want higher consistency. And we're going to talk about data modeling soon, but the way you data model, it allows it to do very few disk seeks, okay? And it restricts you from doing queries that would make it do multiple disk seeks. So you can only read things which are sequentially stored on disk. But there are times when that is too restrictive, okay? And one of it is once you do kind of reporting or analytical style queries. I've stored everything my customer has done, say, watch this movie, say for Sky, watch this movie, streamed this, bought Batman, watch this channel, called the call center and complained. What happens if I just wanted to get like a report of what they've been up to, how many times they've watched Batman, how many times they've watched Game of Thrones, all that type of stuff. You could do that in a relational database, assuming that you're at an appropriate scale, okay? You can't do that in Cassandra, okay? You cannot do that. You can't do group by. You can't do aggregates. You're limited by how you can query because you need to denormalize it so your queries are always satisfied by, say, a single partition, okay? A single computer. But what we're going to talk about today is how we can run Spark on top of it. And when we're happy with a slightly slower response time, so if we're talking about real-time analytics, it might be 500 milliseconds, it might be 10 seconds. If we're talking about our batch job to try and work out what our customers are doing and which shows are becoming popular, we might be happy with 6 hours. If you're using Hadoop MapReduce, you're probably happy with 24 hours. And I've made it safe. Who's seen this cartoon? I think this is one. Can you read it? Is it big enough? Yeah. Sorry, it's inappropriate, but I scribbled out the bad bit. Okay, but essentially when you use the type of technologies that scale, they often do kind of screw you over, okay? Because they essentially stop you from querying ways that you previously could. And you get annoyed, and managers inevitably come up to you and ask you for, say, a count, or what's this customer been up to? Or what quite common with Sky was, the police want to know, after a missing person, they want to see what they were done on Sky over the course of 3 days, or a week, or a year, which it actually happens. And you can't do it because you didn't model your data to store it that way. So Spark saves you. So when I built most of my first systems with Cassandra, Spark was not yet popular and there was not yet a connector between the two. So a lot of the times the things I want to show you how to do things with Spark, you have to write programs to do when you do them directly against Cassandra. But from the people who know MapReduce from Hadoop, It's essentially a like-for-like replacement alternative. It is a distributed compute engine. It allows you to take very large data sets, be them from HDFS or Cassandra tables, and do distributed computation on them, okay? And my favorite part about it, actually, my favorite part is it's got a shell, so you can do interactive work. But the other great thing about it is you can do batch analytics, and you can do streaming with the same API. It's not, say, Storm versus Hadoop MapReduce. It's virtually the same programming API, okay? The same infrastructure. And you won't be that cutting edge if you use it. If you're using a popular Hadoop distribution, it's probably already there. But it's gone beyond that. It's actually creeped into products like DataStaxes. So now when you install DataStaxes Cassandra, version of Cassandra, you can have Spark nodes just in there by clicking a button. So you can start doing these type of like analytical queries, okay? You can set it up to do it open source as well if you want. It's split into a number of components, okay? Spark's not a database, okay? You need data, okay? Normally people would use HDFS, okay? In the examples I'm going to show you, we're going to use Cassandra, okay? On top of that is the general compute engine. That's where you're programming Scala, okay? Who here likes Scala? It's nice. It is nice for this type of programming, okay? There are higher abstractions. You can use Spark SQL. You can also do streaming, which is what we're going to concentrate on. There are also machine learning and graph, which we're not going to cover in this talk. The programming model that we get to play with, okay, is called an RDD. And essentially, that's just an abstraction on top of a very large data set. So our puny human minds don't need to worry about the fact it's a large data set, okay? You can turn a Cassandra table into an RDD. You can turn a HDFS file into an RDD. Once you've got it, you can then do lots of operations. And there's more than two. So you can filter and flat map, and then you can do things which are going to cause shuffles, like group bys. Nothing happens in Spark when you do that, okay? It doesn't suddenly kick off computation. It's only when you actually do something which is visible, like a side effect. That could be saving it back to a file. It could be putting it into Cassandra. It could be, I don't know, mailing it to your mum. That's when Spark actually works out the most efficient way to actually do those 15 maps that you did separately, okay? It'll squash them all into one and work out the most efficient way. A couple of other things to note is after you've computed an RDD, after you've actually done some computation, you can cache them. What that means is to say, by default, it doesn't cache anything because you imagine it's very big data sets and you've only got so much memory inside your Spark computation cluster. But if you're going to reuse the same one over and over again, you can cache it, okay? So you can take some data from Cassandra, do some computation, leave it in memory inside your Spark cluster, and then continually reuse it. Anyone seen Spark word count? Anyone seen Hadoop MapReduce word count? So it's pretty nice in Spark. I didn't have enough slides to put on the MapReduce one. Okay, but essentially here, this is what an RDD is. You don't have to put the types in Scala, but I did just like really show people what an RDD is. What you can then do is do these operations. So we're taking a file from HDFS. You can then split it, by space. You can then map it into a tuple, which is the word, and then one, and then you can reduce by key, okay? And that would be and that is essentially a distributed word count. I have one version of this presentation which actually does 6 different word counts, some from Cassandra, some from socket streams, and all sorts, but you're only getting one today. Because it's quite a short talk, we're actually going to talk just about the other side, so this side, so Spark streaming. So if you're doing batch processing, you can make it as big as you like. Okay, we can as much data as you can fit in Cassandra or HDFS, you could run some type of batch processing on top of it. There is a limit with, say, stream processing because you've got to be able to consume it within a certain window. Okay, and that's basically what Spark streaming is. It takes your stream of data. Where does your stream of data come from? I don't know, a queue, Kafka, 0MQ, a socket, Cassandra, and it breaks it up into lots of little chunks that look just like RDDs. And then when you kind of do the same kind of programming, your flat mapping, your mapping, your filtering, it actually does it every, say, window, and you pick that window. So the smallest is, say, every 500 milliseconds. So what we can do is we can stream weather data, every 500 milliseconds do some computation, and then we can save the result back to Cassandra, which our dashboard can read from. That's like kind of the end goal. And let's see how we do it. So we're going to I've kind of put in Cassandra data modeling in here too, just because we have to model something to solve this problem. So the most important thing when you're using Spark is how you deploy it and how it partitions data. Okay? If someone says, we support Spark, the first thing you ask them is like, how does it avoid moving data around the network? Okay? And because Cassandra already distributes data very nicely, the Spark connector, which is it's a separate open source project, what it does is it builds what are called Spark partitions. It's confusing, we gave them the same name, out of Cassandra partitions, pieces of Cassandra data that all live on the same node. Okay? So what Spark will do is it'll never start off, doing a bit of computation that would mean getting data from more than one Cassandra node. So then the logical thing to do is to whack a Spark node directly on your Cassandra node. So you'd have the same server, both processes. Okay? If you've got DSE, DataStax Enterprise, this just happens. You don't have a choice in the matter. If you're deploying this kind of infrastructure yourself with the open source versions of the project, you just make sure this is the case. And what you typically would not do is put a Spark node on a node which is servicing, your customers. Okay? You designate these on your analytical Cassandra nodes. This is the batch version, my awesome architecture diagrams. And this essentially says, whether data comes into Cassandra, batch process takes raw data out, does some fancy stuff, written in Scala, save it back, and then read it directly from Cassandra for, say, our dashboarding. We're not going to do that. We're going to do the streaming version. So it's not going to go into Cassandra, out of Cassandra, into Cassandra. It's just going to come in through our stream. We're going to save the raw data for later batch analytics if we want to do them, but we're also going to build up some aggregate tables to draw some fancy graphs to impress managers. What does the raw data look like? I did not make this up. This is real raw data that you can go and get from online, historical data for many places. This is what a Cassandra table looks like. It shouldn't look... Does it look familiar? It probably looks familiar, okay? The language in which you interact with Cassandra is very similar to SQL, but not quite the same. Okay, you've got some more types. You've got different types that encourage you to denormalize, like maps and sets and things. But let's have a look at this. So we've got a weather station, okay? So this piece of data is going to be associated with a particular weather station. We've got some time, okay? We've got the year, month, day, and hour. So this data model is implying that we're not going to receive more than one piece of data for a weather station per hour. Okay? Then we've got loads of weather stuff. So we've got, what have we got? Temperature, the hourly precipitation, the 6-hourly precipitation, which way the wind's going. Okay, this is the raw data that we don't want to throw away. We want to keep it just in case we want to do batch analytics. Most of the people I speak to who do stream analytics always want to be able to reproduce the same results with batch analytics just in case. Okay? Especially if it's doing billing or anything like that. So they don't trust their stream analytics quite enough to actually throw away the original data. Not to mention, you might decide you want to process it in a certain way, like a different way in the future. Right, we're going to have a look at Cassandra primary keys. The only thing hard about working with Cassandra is picking the primary key. That's the only way you can kind of go wrong. Okay? The first part of the primary key, so this bit here, the weather station, okay? That was the partition key. That decides that all data for a particular weather station will fit on a single node. If that's not the case, you partition it some more. So you can actually put other fields in here, okay? We could have put the year in there. The rest of it is a bit like Google Big Table. We get to pick how it's ordered on disk. So it's actually going to be ordered by year, month, day, hour. So it's actually going to be ordered in time, okay? The other thing we do is we flip it round to descending rather than ascending. Just so if you do a limit query in Cassandra, it gives you everything back in order. So you don't need to do things like sorting after you get the data back out of Cassandra, okay? So we can just pick whether we want it ascending or descending, which would depend how you wanted to read it and display it. You think with weather data, you probably want the latest weather first. So there we go. That's the partition key. We all know that. And then the clustering columns. And this is how it's going to look on disk exactly. So first thing on disk, it's going to be the partition key. They're all going to be together. So we know it's all on one node. And then the rest of the data is stored in order, just like that. That's pictures of what I just said, essentially. So the things that were our clustering columns have essentially become the second key. You know when I said map of maps? And then this is just storing the temperature. It would be a bit big if I showed all of the fields, but this is like, say, on the 7th it was -5, on the 8th it was -5.1, on the 9th it was -4.9. And just to reiterate, that means we can do this. We can have a 1,000-node cluster with many petabytes of data, and we can go yoink, right into the right place. And then once we're in the right place, we can then read a slice of weather data by doing a single seek on disk and then a sequential read. So that's what makes Cassandra have its scalable performance. So we go in, we're in the partition, and then we seek to wherever we want. So here we're doing a where clause. So we specify the year, the month, and the day, but then we want a time slice of hour. Now, Cassandra's going to limit you here. It's not going to let us do a range on this, on, say, the day and the hour, because they wouldn't be stored next to each other on disk. So that's the limitation of pure Cassandra, but we're going to solve it all with Spark. This is quite a hard model to deal with at times. And if you used Cassandra a couple of years ago, it is actually the model that you programmed to. It's not anymore. CQL is around 2 years old. You now get to see it as those tables, and when you read it back into your application, it does this. Fancy animation. It essentially gives you it as if it was stored as a table. So you need to understand the primary key. It's hard not to understand it because you can't query it any way apart from how you've structured that primary key. But you do get it back inside your application as if it came from a relational database, that programming model that we're kind of used to. We can also store metadata in Cassandra. So nothing Spark so far. If we just wanted the latest weather data, we could just do this with Cassandra. We've also got a bit of weather station metadata. So again, I put in around 20,000 real weather stations, okay? And we're going to store where it is and the elevation and things like that. Why? Who knows? The next thing we're going to do is build things which cannot be done with Cassandra. The kind of things which you could do with a relational database if the data set was small enough and you had enough patience. We want to build some aggregates. So the first one we want to build is, say, the aggregate temperature. And if we look at the primary key, this is per day. The actual application online keeps the aggregate temperature for the day, the month, the year. And we can basically see the only ones really I'm selecting here are the min and the max. Okay? So that we could do in a relational database. You could certainly not do it in Cassandra. If you had many petabytes of data, you could certainly not do it in a relational database unless you had an awful lot of patience. Another aggregate. So let's say we want the precipitation. So the graph I showed you at the start was actually the daily precipitation. And you can stream loads of data through this and actually keep this up to date. So the UI does actually refresh and constantly get updated from the data in Cassandra. Here, per day, so we look at the primary key. We've got year, month, day for a particular weather station. We're using what's called a Cassandra counter. Okay? That's the magic, which we're going to talk about in just a bit. If we're using, say, an integer inside a database, we'd have to read then write. A Cassandra counter allows us to just increment. So for each weather event that's streamed in, I'm going to show how this works, we can keep incrementing for that day until no more come, and then it will remain static. Assuming we create some magic Spark streaming stuff, we're going to end up with a table like this. Okay? We're actually going to be able to constantly keep these aggregate tables up to date, which means that our dashboards, etc., can just read directly from Cassandra. Okay? You would scale your streaming part of your application based on how much data was coming in, and the rest of your the dashboard application based on how many users you had using it. So this is what we're going to end up with. There's no more double arrows now. The data just comes in, goes into Spark streaming, gets saved as raw data, and the aggregates get saved. So we're going to look at some Scala code now just to see how this works. The full Scala, you can go and run this as well, though. You don't need to write this down. So this is what the data looks like. So there's big files checked in, bad, but they're zipped, which will actually have real data, or there's a load generator for creating random data, somewhat random data. Okay, and the first thing we do is turn this long comma-separated line with all the data into a nice case class. Okay, come across Scala case classes? I wish Java had them. Essentially, it's an immutable kind of POJO. Okay, and we just turn that string into that nice case class. It's got nice names and things. To create a stream with Spark streaming, it's a one-liner again. I haven't shown you how to create a Spark context, but that's just another one-liner. The thing you give a stream is how long you want that micro batch to be. How often do you want the computation to happen? Okay, because you get to really cheap aggregation inside that little window. I'm not going to talk much about Kafka, like where we're streaming the data from. I'm going to assume it's quite irrelevant. The first 2 lines of this are to do with Kafka, but the next 2 lines would be the same regardless of whether we were doing it, getting the data from a socket, getting the data from ActiveMQ, whatever. And again, remember it is that comma-separated value. It's a nice Scala API again. We get to split it. And this is just some Scala magic for creating a case class from an array. Okay? So we instantly there have a stream of case classes, this nice raw weather data. Now, if you remember, RDDs and streams are reusable. So we can use this stream twice. It's actually inside the actual code. It's used many a times. It's used for all of the aggregates. The first thing we can do with this very complicated line of code is to save it directly to Cassandra. Okay? Because the case class matches that table, remember that raw weather data table, you literally just have to put save to Cassandra. And the connector for Spark Cassandra uses implicits to add all of these methods to streams and RDDs and things. So you can instantly go save the data for later batch analytics. Okay? Some of the examples in the one online do use batch analytics. You hit it with a HTTP request and it does a little Spark batch thing and then give you an answer. Remember this aggregate? So this is the code which would actually produce this aggregate. Okay? So we do a map. So we map it to look just like the table. So this is just a tuple in Scala. And we don't need to do anything else. And the answer is, don't we need to use the old values? But because we use Cassandra counters, now Cassandra counter, if you put 5 in it, it actually adds 5. It doesn't turn it into 5. So for all of these events streaming through our thing, constantly are updating it. Okay, so every single message that ends up on Kafka ends up updating a counter in Cassandra. And that's really cheap. That goes directly to that one node and just increments a counter. You know, there's no kind of like, you know, cross all of my data analytics like batch processing there. And then we end up with something like this. So for the real example, you can either get it from files, and there's a way to just import the files and send it all onto the Kafka queue, or there's a way to do dynamic generation. It ends up on a Kafka queue, and then streaming consumes it all, writes it all into Cassandra, and then there's a definitely not pretty dashboard which displays it. I haven't yet added all the aggregates to the dashboard, but essentially you can go in, you can see the weather stations, and then you can go and look at some of the aggregates. My idea about building this example up is to eventually like give people in the audience like little Raspberry Pis, because you can actually get Raspberry Pis which have like little weather stations on, and have people actually being able to upload data into it. But I'm not quite there yet. If you want to go and play with this stuff, it's a near production ready example. It's not just naughty code. Okay, you can happily use this as it's probably the main reference application for Spark and Cassandra integration. Up until now, it's primarily been developed by a genius called Helena. She is a Spark connector, and a Spark connector committer. That's a mouthful. An Akka committer. She works on Cassandra. I've just started adding some stuff now just to make it more visual. So that's pretty much up today. We talked about Cassandra, so I think that was new for most people. So it's a really interesting database if you want to build an always-on system, and it can handle crazy amounts of durable writes, depending if you've got enough money for the hardware. Spark is a really useful tool. I anticipate that everyone who uses Cassandra will eventually use Spark on top of it, even if it's just to fix their broken schema, because they've saved it away and they want to save it a new way or new requirements come in. It's really easy to build a new table from an old table. Stream processing is kind of, I think, a game changer. Previously, it had to be multiple technology stacks, whereas now we can use Cassandra and Spark to do many things. It's our operational database, it's our stream processing, and it's our batch processing. Okay? It's not 3 teams, it's not 3 sets. I'm not saying if you were going to build, say, a BI solution from the start, you would use Spark on top of Cassandra rather than HDFS. But if the data's already in your operational system, there's a really good point to say, let's not extract it and put it somewhere else. Let's do it directly on top. Yeah.
One last question. I noticed online in the Datacenter document, you can configure individual nodes to be analytics nodes. Mm-hmm. And so I guess the idea is that you can have your operational data running and being uninterfered while you do your batch runs on these analytics nodes.
Correct.
But aren't these nodes at the same time going to be updating? What happens if they're being really hammered by the batch processing?
Correct. So this can, if you have say data centers, Cassandra data centers, so designated nodes of different spec, you can absolutely get behind, because the ones which is actually ingesting the data could be your fancy SSD backed blah blah blah, and then you could have some really slow ones. So there's if it's a small period, then Cassandra just catches up. Okay, the guys who are handling the writes, they store it until that guy acknowledges it, for default by 3 hours. If it's a bigger problem than that, then what you do, you need to go to the nodes, which are, say, your analytics nodes, and tell them, hey, you definitely were, behind at some point. Go and get the data, and it actually requests, and it uses Merkle trees to repair the data. And there's a metric that comes out of Cassandra, which is called dropped mutations, which is exactly
what it doesn't rebuild the whole node, it recovers. It
recovers. So what it does, because it takes the data and essentially builds up a Merkle tree of, that table, and on that table there, and then tries to stream over the smallest possible data. Because you can't have many terabytes on a Cassandra node, so even the Merkle tree can be very big. So yeah, you don't have to rebuild the whole node. It can recover itself. Thanks very much.